Today, we will be looking for the holy grail of flight, the aeroplane. Oh, there it is. That was easy.
So now that we have our airplane, you might be wondering how we get it to fly. The secret, of course, is lift. In this video, we'll cover the basics of how an airplane uses lift to get off the ground. But before we delve too deeply into that, let's cover some basic physics. You might have heard of Newton's first law of motion, which can be paraphrased as, an object at rest tends to stay at rest, unless acted upon by some force. Kind of like me on a Saturday morning. Anyway, let's look at the forces on this aircraft. First, we have that infamous law of gravity, which pulls the plane towards the Earth. As you might expect, there is some additional force that's keeping the plane from falling through the Earth. The ground will impart a force back onto the airplane equal to the plane's weight on the ground. If Bob here decided to stand on the runway and a plane ran over him, he might exclaim, "Help! The plane is crushing me!" Silly Bob. He's technically being crushed between the plane and the ground. Since there are only two forces acting on this plane, weight and the ground's reaction force, it will sit happily on the runway, enjoying a balance of forces and going absolutely nowhere. On the other hand, passengers and Bob may not like this idea. So let's add some engines to this poor grounded plane to get it out of its happy balance. To take off, a pilot will typically push the throttle all the way forward, which is similar to what drivers would call flooring it.
Floor it?
Yes. No! Don't floor it!
Let's add the force of thrust to our awesome airplane, which will cause it to move forward and down the runway.
And there was much rejoicing.
Now, there might be a bit of force due to wind resistance, or drag, but it's so small at this point, the powerful engines laugh in its gusty face. Since the thrust is so powerful, it starts to barrel down the runway faster and faster. The passengers are getting excited, but the growing anticipation fell flat on its face. The plane isn't taking off. Thankfully, this is a really long runway, because we forgot to add the force that will cause the aircraft to rise into the air. Lift. As you are probably aware, the vast majority of lift comes from the plane's wings. As air rushes over the wings, it generates an upward force. The faster the plane is traveling, the more air flows over the wings, and therefore more lift is generated. At a high enough speed, there is enough lift to cancel out the force of gravity or weight. At this point, the pilot will cause the aircraft to tilt upward, which creates significantly more lift, and the plane is pushed into the air. Hey, look, Bob's coming with us. How did I get here? If you recently flown on a plane, you might remember hearing the phrase, "We are now at cruising altitude." What this means is that the plane is now once again happily enjoying a balance of forces. We have lift acting upward, drag acting backward, the weight of the aircraft acting downward, and thrust acting forward. But how is lift created? Let's break this magical force down bit by bit. First, let's take a slice of this wing. This two-dimensional cross-section is typically referred to as an airfoil. We'll designate the air coming in with blue arrows and label it as V for velocity, or airspeed. Now, some of you might have heard the equal time theory when you were younger. I know when I was younger, it was explained to me that lift is generated because the air on top has further to travel than the lower surface. So the air on top has to speed up in order to catch back up to the air on the bottom. Sadly, just like my urinary incontinence, this theory just doesn't hold any water. How do we know? Well, imagine we had a funky-shaped wing like so. We could give the airflow a roller coaster ride, meaning if this equal time theory were true, this wing would generate a ton of lift. Though, as you might have guessed, this wing fails at producing any meaningful lift. So, how does lift get generated? If you took a ping pong ball and blew on it from below with a hairdryer, you'd expect the ping pong ball to travel upwards, right? Well, this is a type of lift. I'm sure at one point or another, you've held a cupped hand out the window of a moving car, and you've noticed that if you hold your hand at the right angle, the incoming wind will push your hand upwards. This force is also lift. To explain lift as simply as possible, it's when you have higher air pressure at the bottom surface and lower air pressure on the upper surface. When you hold your hand at an angle outside of a moving car, air is being rammed into the bottom of your hand, pushing it upward and backward. The same idea applies to a kite. If you hold a kite up at an angle and run into the wind, the air will be pushing the kite upward and backward. But since you are holding the kite with a string, you are counteracting the force of the wind, and so the kite is happily enjoying a balance of forces. A fan, or helicopter rotor, works in a similar way. The only real difference is that the blades on the helicopter rotor move through the air in a circular motion rather than linear. As the blades spin faster and faster, each blade generates a bit of lift, until eventually the helicopter rises into the air. So, here's a picture of a plane. Just like putting your hand outside the window of a moving car, as air flows over the wing, it will be forced downward, resulting in an equal and opposite reaction. But there's a little bit more to lift than air blowing upwards on an object. After all, a plane's wings are typically parallel with incoming air. Now that you understand the basics of lift, let's investigate why a plane's wings are shaped the way they are. Remember, the basic principle of lift is that there is higher pressure on the lower surface and a lower pressure on the upper surface. Have you ever poured a pitcher of gravy only to have the gravy run down along the side of the pitcher rather than down onto your mashed potatoes? Is this gravy defying gravity? Of course not. The interesting thing about fluids is that they like to stick along a surface. And yes, air is a fluid too. It's just not a liquid fluid. So let's look at a two-dimensional cross-section of a wing, typically called an airfoil. It's drawn at an exaggerated angle here so as to better clarify what's going on. If we have air flowing over this airfoil, the air on the top surface will initially want to go straight off to the right, and the air on the bottom surface will be forced downward. However, if you think about it, if there's no air in this area on top of the wing, it would theoretically be a vacuum. No, not a vacuum cleaner. I mean vacuum as a result of the lack of air pressure, kind of like what you'd experience at very high altitudes or in space. So, if we have an area of very low air pressure here, the air will naturally want to flow to this region. In essence, the air is getting sucked downward back towards the wing. As a result, the airflow will look a bit more like this, with an area of low pressure near the top surface of the wing. From this perspective, you can recall that lift occurs when there is higher pressure on the lower surface than on the upper surface. For example, let's consider how that vacuum cleaner picks up cookie crumbs from a carpet. A vacuum cleaner works by creating an area of low pressure, causing the surrounding air to be sucked into the hose. If the vacuum hose gets close enough to an object on the floor, it will create an area of low pressure just above it. If the hose is moved even closer to the object, eventually the pressure difference between the lower surface and the higher surface becomes so great that the lift effect starts to overpower the weight of the cookie crumb. When this happens, the object is lifted into the hose. Let's look at the magical force of lift from another angle. Newton's third law of motion states that, for every action, there needs to be an equal and opposite reaction. Do you remember before when I mentioned that when a plane is sitting on the runway, the weight is acting down on the ground, and there's an equal and opposite force pushing back on the plane? I remember. The same thing happens with the airflow over a wing, though it's not quite as easy to envision. Let's draw another airfoil. As air comes in, it will want to flow around the wing, like so. Remember that a fluid likes to stay near the surface of the wing due to the area of low pressure at the top surface. The total force of the incoming air is perfectly horizontal in this diagram, while you might notice that the air leaving off the trailing edge on the right tends to be moving slightly downward. Note that there's now an extra downward force component in this picture that didn't exist before the air came into contact with the wing. Because of Newton's third law, there must be an equal and opposite reaction. In this case, the reaction is a slight upward force. This is lift. In this video, we discussed the basic principles of lift. If you're interested in some other applications of the magical force of lift, feel free to check out the bonus video on the Magnus effect. Now that you're familiar with the basics, next time you're on a plane, try to get a window seat and watch the wing as you fly to your destination. While you can't see the air flowing over that wing, at least now you can imagine it. Or don't. I'm not your boss. Thanks for watching.